What if a spacecraft older than most people watching this video just whispered something back to Earth that no scientist on this planet was fully prepared to hear? What if that whisper traveled for 19 hours through the cold silence of space, crossed a boundary humans have never physically touched, and arrived carrying a frequency that should not exist in the way our best models describe it? Something is happening at the edge of our solar system right now, and almost nobody is talking about it the way it deserves to be talked about. Before I take you deeper into this, do me one small favor. Hit that like button, tap subscribe, and share this video with one person who still looks up at the night sky and wonders what is out there, because what I am about to explain is one of the most quietly astonishing moments in the entire history of space exploration, and you deserve to hear it in full. Voyager 2 is not close to us. It is not near the moon. It is not near Mars. It is not near Jupiter. It is over 13 billion miles from Earth, sitting in a region of space so far away that when NASA sends it a command, that command travels at the speed of light for 19 straight hours before the spacecraft even receives it. Then the reply takes another 19 hours to come back. So every time an engineer types an instruction and presses send, they have to wait almost 2 entire days to find out whether the spacecraft heard them, understood them, and acted on them. And on August 4th, 2026, the answer came back. It worked. NASA's Jet Propulsion Laboratory just confirmed the success of a plan. The team quietly nicknamed the Big Bang. It was a maneuver so risky that some of the engineers involved said they did not sleep the night they sent the command. It was a single simultaneous power adjustment across multiple systems on a spacecraft that has been running for 49 years on a nuclear battery that loses a small amount of energy every single year. There was no room for mistakes. There was no way to physically fix anything if something went wrong. And yet, when the confirmation signal finally reached Earth, after its long journey through interstellar darkness, the numbers were clean, the systems were stable, the instruments were alive. Voyager 2 had just been given at least another year of life beyond what anyone thought possible. And that is not even the most extraordinary part of this story. The extraordinary part is what Voyager 2 is doing with that extra year, because the signals it keeps sending back are hinting at something about the space beyond our solar system that scientists are still struggling to explain. Let me take you back to the beginning so this all makes sense. Voyager 2 launched on August 20th, 1977. That is not a typo. 1977. It launched 17 days before its twin, Voyager 1, even though it was named number 2. And the reason for that strange numbering is simple. Voyager 2 was placed on a slower, longer path, so it could take advantage of a rare planetary alignment that happens only once every 176 years. That alignment made it possible for a single spacecraft to visit Jupiter, then Saturn, then Uranus, and then Neptune, one after another, using each planet's gravity to slingshot toward the next. NASA called this the Grand Tour. Voyager 1 was sent on a faster path that only included Jupiter and Saturn, giving it a head start into deep space. Both machines were designed for a mission that was supposed to last 5 years. Just 5. That was the promise. That was the plan. And now, 49 years later, both of them are still transmitting. Let that sit for a second. A machine built with early 1970s technology, launched before most personal computers existed, before smartphones, before the internet as we know it, is still working. Still listening, still measuring, still sending information back to a species that has changed almost beyond recognition since the day it was launched. Voyager 2 flew past Jupiter in 1979. It reached Saturn in 1981. It visited Uranus in 1986. It reached Neptune in 1989. And to this day, no other spacecraft in human history has ever flown past Uranus or Neptune. Everything we know from direct observation of those two ice giants came from the cameras and instruments on this one aging probe. Take a moment to appreciate that. Every photograph, every reading, every close-up piece of data we have on 2 entire planets in our own solar system comes from a machine built with slide rules and blueprints, still running on the far side of everything. But surviving that long comes with a cost, and that cost is power. Voyager 2 does not use solar panels, because at these distances, the sun is barely a bright star, not a source of energy. Instead, both Voyagers use something called radioisotope thermoelectric generators. These are essentially nuclear batteries. Inside them, a small amount of plutonium slowly decays, producing heat, and that heat is converted into electricity. When Voyager 2 launched in 1977, its generators produced about 470 watts. Every year since, as the plutonium has continued its slow decay, the power output drops by roughly 4 watts. Do that math for nearly half a century and you begin to understand the situation. Voyager 2. Today runs on a fraction of the power it started with. Every single watt is precious. Every choice about what to leave on and what to shut down is a serious engineering decision made by a small team of people who have devoted large parts of their careers to keeping this spacecraft alive. Some of them have worked on Voyager for 30 or 40 years. Some of them are younger than the mission itself. All of them understand that the machine they are managing cannot be replaced. Over the years, they have carefully turned off heaters. They have shut down backup systems. They have deactivated science instruments one by one, always following a plan that balanced what was still returning valuable data against what had already completed its purpose during the planetary flybys. Voyager 2 originally carried 10 science instruments. By the start of 2026, only 3 were still running. The magnetometer, which measures magnetic fields. The plasma wave subsystem, which listens to vibrations in the invisible ocean of charged particles around the spacecraft. And the cosmic ray subsystem, which detects the extremely high energy particles that stream through this galaxy from ancient exploding stars. And without the Big Bang, the cosmic ray subsystem was scheduled to be shut off before the end of this year. And I want you to pause and picture what that means for me right now, because there is something important I need you to do while it is fresh in your mind. If this story is pulling you in, if you can feel the weight of what these machines represent, drop a comment below with just one word: alive. Just that. Because that is what Voyager 2 still is against every rule of engineering and every reasonable prediction of physics. And while you are down there, hit subscribe if you haven't already, because this channel is where stories like this get told without the noise, without the shouting, and without the shortcuts. Now let me tell you exactly what the Big Bang actually was, because a lot of headlines have used the phrase without really explaining it. Voyager 2 has small thrusters that it uses to keep its antenna pointed at Earth. Without those thrusters, the antenna drifts, the signal is lost, and the mission ends forever. But those thrusters rely on fuel that flows through narrow lines, and if those lines get too cold, the fuel freezes and the thrusters stop working. So the spacecraft has always used small heaters to keep the fuel lines warm. Those heaters consume power. And in a spacecraft that loses 4 watts every year, power spent on heaters is power that cannot be spent on science. The engineers came up with a clever idea. They realized that certain other devices on the spacecraft, when powered on, would naturally give off enough waste heat to keep the fuel lines warm on their own. In other words, they could use hardware that was already useful for another purpose to also do the job of the heaters. If they could switch off the dedicated heaters and switch on the alternative devices at the exact same moment, they would save nearly 10 watts of power without letting the fuel lines cool down to dangerous levels. 10 watts might not sound like much. In your house, 10 watts is a small LED bulb. But on Voyager 2, 10 watts is roughly 2.5 years of natural power decline. 10 watts is the difference between shutting off a science instrument this year and keeping it running for another 12 months. 10 watts is the difference between silence and data. But the risk was enormous. The swap had to happen simultaneously. If the new devices did not come online fast enough, the fuel lines would begin to cool, and once thermal damage started, it could not be undone. There was no way to send a technician out to check. There was no way to reset anything by hand. There was only the command, the signal, the 19-hour wait, and the hope. So the team practiced. They ran tests on Voyager 2 during May and June of this year, choosing Voyager 2 first because it is closer to Earth than Voyager 1, which meant a slightly shorter wait for each round of confirmation. They chose Voyager 2 also because it had a small amount more power available than its twin, making it the safer place to try something dangerous. The tests worked, the full procedure was scheduled, the command was sent, and on August 4th, 2026, the confirmation came back through the Deep Space Network. Voyager 2 was still alive. Its 3 science instruments were still running. Its fuel lines were still warm. The Big Bang had succeeded. In the coming months, the same procedure will be attempted on Voyager 1, which sits over 15 billion miles away and takes more than 23 hours to receive a single signal. Now, here is where the story stops being about engineering and starts being about the universe itself. Because Voyager 2 is not just floating out there. It is doing something no other object built by human hands can do. It is measuring the space beyond our solar system from the inside. And to understand why that matters, you have to understand something called the Heliosphere, because the Heliosphere is one of the most important structures in our entire cosmic neighborhood, and almost nobody is taught about it in school. Imagine our sun as a small furnace at the center of a giant invisible bubble. That bubble is not made of glass or metal or gas in the ordinary sense. It is made of the solar wind, a constant stream of charged particles that pours out from the sun in every direction. This stream pushes outward and outward until it eventually meets the pressure of the space between the stars, the interstellar medium. Where those two pressures balance, the bubble forms its outer edge. That edge is called the Heliopause. Everything inside the Heliopause is the sun's territory. All 8 planets, the asteroid belt, the Kuiper belt, comets, dwarf planets, everything you have ever seen in a solar system diagram sits inside this bubble. Outside the heliopause is interstellar space. This bubble is not just a curiosity, it is a shield. The galaxy is filled with cosmic rays, extremely high-energy particles, that come from exploding stars, colliding neutron stars, and other violent events far beyond our solar system. Without the Heliosphere blocking most of them, life on Earth would be exposed to far more radiation than it is now. The sun creates this shield, the sun maintains it, and the outer edge of it defines where our solar system truly ends and the rest of the galaxy begins. For most of human history, we knew about this bubble only through math and indirect observation. We could infer its rough shape, we could estimate its size, but we had never actually been inside it and then outside it. We had never crossed the wall, until Voyager 1 did on August 25th, 2012, and then Voyager 2 did on November 5th, 2018. When Voyager 1 crossed the heliopause, its plasma science instrument was no longer working, which meant it could not directly measure the plasma around the boundary. When Voyager 2 crossed, its plasma science instrument was still alive, and for the first time in human history, a working plasma instrument was recording what happens when a spacecraft leaves the sun's bubble and enters the space between the stars. What it measured did not match the predictions. Before I tell you what those measurements were, let me say this quickly. If you are still with me here, you are the kind of viewer this video was made for, and I want to ask you something small in return. Turn on the notification bell so you never miss the next story, because I have several more coming that go even deeper into what these old spacecraft are finding at the edge of everything we know. Share this video with someone who told you space exploration is boring, because after this, they will not say that again. Now back to what Voyager 2 measured. The plasma just outside the heliopause turned out to be scorching hot. The instrument recorded temperatures between 30,000 and 50,000 Kelvin. Read that number again. 30,000 degrees. 50,000 degrees. In a region of space that scientists had long assumed would be cold, calm, and sparse. Interstellar space was supposed to be quiet. What Voyager 2 found was a plasma so hot that even the modelers had to sit down and rework their assumptions. But hot, in this case, does not mean burning like a fire. In space, temperature and density are two very different things. The interstellar plasma is extremely thin, meaning there are very few particles per cubic meter, but each of those particles is moving at very high speed. That high average speed is what registers as high temperature. If you were somehow floating in that plasma without a spacesuit, you would not feel heat. You would freeze. There simply are not enough particles to transfer meaningful energy to a large object like a human body. But for a scientific instrument designed to count and characterize individual particles, that thin, fast plasma is a treasure map, and Voyager 2 was reading it. Then it got more interesting. The heliosheath, which is the region just inside the heliopause where the solar wind slows down, before hitting the boundary, turned out to have a structure different from what the models had predicted. The termination shock, which is the point where the solar wind first begins to slow from supersonic to subsonic speeds on its way to the boundary, was in a different shape and location than expected. The heliopause itself, which had been imagined as something like a clean line in a diagram, was in reality a complex, layered transition. Properties did not shift all at once. They shifted across multiple zones. The wall between our solar system and the rest of the galaxy is not really a wall. It is a series of thresholds, each with its own personality, each with its own strange behavior. And Voyager 2 walked through every one of them with its instruments switched on. Now, in August 2026, with the Big Bang procedure keeping the cosmic ray subsystem alive, 3 instruments are still measuring 3 different aspects of that region of space. The magnetometer is mapping the magnetic field of interstellar space. Yes, there is a magnetic field out there, carried through the galaxy by plasma that was blown outward by dying stars over billions of years. Voyager 2 is measuring the direction and strength of the field in real time. The plasma wave subsystem is detecting oscillations in the plasma around the spacecraft. Those oscillations reveal the density of electrons in the medium, which in turn tells scientists how thick or thin the local interstellar material really is. This is the same type of instrument that, on Voyager 1, has been picking up a persistent, low, continuous hum since 2017. That hum is a plasma wave signal generated by the interstellar medium itself, and it has allowed researchers to map how the density of that medium changes as the spacecraft continues to move away from the sun. It is, in a very real sense, a frequency coming from outside our system, one that no one on Earth has ever heard before through any other instrument. The cosmic ray subsystem, the third and most fragile of the 3, is measuring the galactic cosmic rays streaming in from deep space. And this is the instrument that would have died this year without the Big Bang. This is the instrument the entire risky maneuver was designed to save. Because measurements from outside the heliosphere tell scientists exactly how much protection the sun's bubble is actually giving to life inside it. If you want to know how much shielding our planet is receiving from the galaxy's deadliest radiation, you have to measure the radiation from both sides. Voyager 2 is the only object we have on the outside. Take that away, and we lose half the picture. There is more. The sun itself changes over an approximately 11-year cycle. When the sun is at its most active, its solar wind is stronger and the heliosphere inflates slightly. When the sun is quiet, the heliosphere shrinks a little. Voyager 2, from its position on the other side, can see how the cosmic ray flow changes as the bubble expands and contracts. Nothing else in human history has ever provided this outside in view of our own solar system. And here is another surprise the data is revealing. Before the Voyagers crossed the boundary, most scientists imagined the heliosphere as a comet-shaped structure with a rounded front and a long tail streaming behind it in the direction opposite to the sun's motion through the galaxy. That idea guided textbooks for decades, but Voyager 1 crossed the Heliopause going roughly north, and Voyager 2 crossed it going roughly south, and both crossings happened at similar distances from the sun. That similarity strongly suggests the heliosphere might be far more spherical than we assumed, more like a rounded ball than a stretched teardrop. And yet, at the same time, the two crossings behave differently in a very specific way. Voyager 1 recorded dramatic magnetic field fluctuations right at the boundary. Voyager 2 recorded almost none. The heliopause is shaped one way in one direction, behaves another way in another direction. It is not a symmetric object. It is not a smooth ball. It is something more complicated, and we only have two direct data points to work from, two crossings in the entire history of humanity, and the picture already refuses to be simple. This is why every extra day of Voyager 2's life matters. This is why 10 watts saved by a group of engineers in California, whispered across 13 billion miles of cold space, is not just a number on a spreadsheet. It is a doorway kept open a little longer to the only real measurement humanity has of what lies beyond our own bubble. Now let me stop for a moment and speak to you directly, because you have made it this far, and that means something to me. If this video is teaching you something you didn't know an hour ago, if it is making you look at the sky a little differently, then send it to someone who has stopped feeling wonder. Send it to someone who thinks the world is small. Send it to someone who thinks nothing new is happening. Because something new is always happening. It is just often happening in the quiet corners of the universe, 13 billion miles away, at a signal rate of 160 bits per second. Yes, 160 bits per second. That is the speed at which Voyager 2 sends its data back to Earth. It is comparable to a dial-up modem from the 1990s. A single modern smartphone photograph, if you could somehow beam it from Voyager 2 to Earth at that rate, would take hours to arrive. That is the trickle of information carrying the only direct interstellar measurements humanity has ever made, and the signal itself is faint. Voyager 2's radio transmitter uses about 23 watts of power, similar to the little bulb in the back of a refrigerator. That signal, after traveling more than 13 billion miles, arrives at Earth so weak that only the enormous dishes of the Deep Space Network, spread across California, Spain, and Australia, can catch it. Multiple antennas often combine their signals to detect the fragile whisper coming in. Engineers guard every bit of that data. They pick and choose which data blocks to prioritize, which to delay, which to store on the spacecraft's aging solid-state recorder for later. Everything is a compromise. Everything is a careful trade between what is scientifically valuable and what is technically possible. And now, thanks to the Big Bang, they have more time. They have at least one more year of the magnetometer, one more year of the plasma wave subsystem, and one more year of the cosmic ray subsystem. If everything continues to go well, some of the engineers believe they may be able to keep at least one instrument alive into the 2030s. Voyager 1 will receive the same treatment in the coming months, and there is a symbolic milestone on the horizon. On November 18th, 2026, Voyager 1 is projected to reach exactly one light day away from Earth. That means a signal from Earth, traveling at the speed of light, will take a full 24 hours to reach it and another 24 to return. 2 whole days for a round trip. The first human-made object ever to reach that mark. Voyager 2 will not reach one light day until 2035, and honestly, most engineers do not expect it to still be operating by then. But Voyager 2 has been surprising people for 49 years, and it might keep doing so. This is what is at stake in every command, every wait, every whispered reply. It is not about statistics on a page. It is about the fact that Voyager 2 is physically inside interstellar space, not looking at it through a telescope, not sensing it indirectly through particles that drift back home, physically inside it, physically surrounded by the interstellar medium, measuring its temperature, its density, its magnetic field, its plasma waves from within. Nothing else on Earth or off it can do this. No other spacecraft is on the way to duplicate it. Even if a new mission were designed and funded tomorrow, it would take decades to reach the distances Voyager 2 has already covered. There is no backup. There is no substitute. And so when the signal came back on August 4th, 2026, confirming the Big Bang had worked, it was not just an engineering victory. It was the extension of the only living connection humanity has to the space beyond the sun. A frequency from outside our system, faint and steady, still arriving. And Voyager 2 keeps going. It is moving through interstellar space at roughly 34,000 miles per hour. It is bathed in a plasma hotter than anyone predicted. It is surrounded by a magnetic field carried across the galaxy by ancient stellar winds. It is being showered by cosmic rays from events that happened millions of years ago in distant corners of the Milky Way. And it is listening. It is measuring. It is quietly sending back information that our best models are still trying to catch up with. Think about the people involved in this for a moment. Some of the original Voyager engineers have passed away. Some are retired. A new generation now stands in their place working with the same commands, the same code philosophies, the same care. They inherited a machine older than they are, and they are keeping it alive with almost sacred dedication. When they sent the Big Bang command, they were continuing a conversation that began in 1977, when a much younger version of humanity looked up and decided to send a piece of itself out among the stars. That is what Voyager 2 really is. It is not just a spacecraft. It is a message from one generation of humans to whatever generations come next, saying we tried, we reached, we listened, we did not stop. And the frequency that keeps coming back from just beyond the edge of our solar system is not only a scientific reading, it is a reminder that the universe is stranger, richer, hotter, more layered, and more surprising than our models have ever fully captured. A reminder that even something built with the technology of the 1970s can still teach us in the 2020s. A reminder that a small team of engineers working with careful math and quiet courage can extend the reach of humanity itself by 10 watts and 1 year at a time. So the next time you look up at the night sky, remember that somewhere out there, past every planet you can name, past the last outer edge of the sun's protective bubble, a small machine older than most of the people on Earth today is still awake, still whispering, still measuring things that no one else can measure, still telling us that the universe is not finished being understood. NASA confirmed the signal. The Big Bang worked. Voyager 2 keeps going, and the frequency from outside our system keeps arriving, one faint bit at a time, one 19-hour journey at a time, carrying with it the quiet, patient, extraordinary message that humanity, in its own strange way, is not alone in what it can reach. That is where Voyager 2 is tonight. That is what it is doing tonight, and thanks to what happened on August 4th, 2026, it is going to keep doing it a little longer. Long enough, maybe, for us to finally start hearing what it has been trying to tell us all along.